Thank you very much, Anastasia. So, firstly, thank you very much to Anastasia and to Akil for the invitation to come and speak to you. I called the seminar, the webinar, Biological Applications of Optical Tweezers. Then I had to put a few in front of that, because if I were to talk about every possible biological application of optical tweezers, we'd probably still be here next year. So, very much a selection of possible applications. There are, of course, many, many more, and I'll touch on here. Now, I was very pleased when actually Akil contacted me to give this webinar, because as Anastasia said in the introduction, this is not necessarily just a seminar about my work, although there will be some of my work in there, but also a look at some of the other research that's going on and have a wider perspective. And at the time when Akil contacted me, it actually matched very nicely to something I was working on. I was writing an article with Lynn Patterson of Heriot-Watt University, who I think may be attending the webinar today as well, for a forthcoming roadmap issue of the journal JPhys Photonics. This is being edited by Giovanni Volpe, Onofrio Amerigo, and Helena Rubinstein Dunlop, and contains a large number of articles, which the aim of each of them really is similar to the aim of this seminar. It's to give a wider overview of the state of the art of particular topics, particular applications of optical tweezers, in this case, with a view to the future. So Akil's invitation arrived at the same time I was writing this with Lynn. And so this seminar was very much based on what we were writing in that article, which was due for publication later this year. So as well as watching this back online afterwards, hopefully in a few months' time, you'll be able to read that article, which in fact contains more examples than I'm able to fit in here in this presentation today. So my very rough plan for the webinar is, firstly, I'll introduce optical tweezers. Now, there'll be many people watching this who are working in the field, very familiar with optical tweezers. They work in optics, I've come across them before, but I'm also aware, particularly in talks like this, we have particularly younger researchers and PhD students who aren't necessarily working in the field, and it may be new. And obviously we want to include everyone, and so I'm going to start the seminar with a little introduction to optical tweezers, just to set the scene, and explain why they're useful, particularly for applications in biology, and let's look at a couple of the very early, very first applications of optical tweezers to biology. I'll spend a little time discussing some of the experiments we've done at UCL. There. Well, I hope you'll find them interesting. It's a small, it's a part of the wider research program we have in the optical tweezers group at UCL. And then I'll mention a couple of what I call the future challenges, sort of a state-of-the-art application that have come from other research groups, to give us sort of a wider view of the field and where it might go in the future. And throughout all this, what I'd very much like to do is highlight the contribution of especially the younger researchers, the PhD students and postdocs who do this. So I'm sitting here in the comfort of my spare room, giving this talk to you and presenting these results, but these results are retained by early career researchers, PhD students and postdocs at the beginning of their career, doing this work, and it's very important to highlight their contribution, because they're the people who spend the time in the lab or do the work doing the simulations. So throughout the talk, I will be mentioning some names of the people who have actually derived these results. So, optical tweezers. And when we mention optical tweezers, there's one name that is always attached here. So Arthur Ashkin, of course, as you see in the picture here. Nobel laureate Arthur Ashkin awarded the Nobel Prize in 2018. He was a half share in that year. And his award citation was for the optical tweezers and their application to biological systems in particular. This was highlighted in the Nobel citation. And the very famous paper in which the optical tweezers was first reported experimentally, the single beam gradient force optical trap, is referred to in the title. This paper, published in Optics Letters in 1986. It is still, I think, the most highly cited paper in Optics Letters, even today. But as well as this paper, it's fascinating to trace the trajectory of Ashkin's research from the first papers that are sort of evaluating the optical force on particles in the early experiments, that show propulsion of microscopic particles along a laser beam, to optical levitation experiments, to trapping in a counter-propagating trap, until we arrive at the very famous paper from 1986, where three-dimensional confinement using a single beam, what we call optical tweezers, was demonstrated for the first time. So what is an optical tweezer? How does it work? As I said, this will be familiar to many already, but some people may be coming to this for the first time, so I'll give a short explanation. Two short explanations, if you like. One, if we consider our particles to be very large compared to the size of the wavelength of the light that we use for trapping, and one where the particles are fairly small. Actually, I just go back to the abstract of Ashkin's 1986 paper. He says he observes trapping over the entire range of particle size from 10 microns, so it's very much larger than the wavelength of the laser light being used, down to 25 nanometers, very much smaller. So we have those two extremes of the size range there in the abstract of the first paper. So if we consider that the large particles, first of all, in this case, we consider our laser beam to be composed of rays. Okay, so if you look at the figure top left here, this is supposed to show the Gaussian intensity profile of our laser beam, and just considering a single ray here, it is incident on I've labeled a polystyrene microscope. It is very commonly used in optical tweezers experiments. They're small, they're very regular, very easily obtainable. And as the ray crosses the interface from the suspending medium, which is typically water, into the object to be trapped, polystyrene here, going from a lower to a higher refractive index, we have a change in the trajectory of the ray. We have refraction, so a lensing effect. And similarly, as the ray crosses the particle, as it leaves as well. So we can see that this ray here, its direction is deviated by refraction, the interface between the particle and suspending medium. Now, the ray carries momentum, and momentum vector quantities, magnitude and direction. Since the ray has changed direction, there must be a transfer of momentum to the ray, and if momentum is conserved, there must be an equal and opposite transfer of momentum to the object here. So these two arrows labeled delta P, so one down here especially for the transfer of momentum to the ray, and this one the transfer of momentum to the object from that ray. And so if we sum the contribution from all the rays striking the particle, then they will all contribute a transfer of momentum to the particle. But perhaps what we'll see here is that because we have a gradient of intensity, right, so we account for this by the intensity, the gradient of intensity of the rays striking the object. We sum up all these, and there's a net transfer of momentum which pulls the particle across the Gaussian profile of the laser beam until it ends up on the axis, and if it moves across the other side, it feels a transfer momentum force that pulls it back onto the axis as well. And this is what Ashkin observed in the earliest experiments with a laser beam propagating through a tank containing microscopic particles. They were drawn onto the axis by this lensing effect and then propelled the light. They were propelled along it by the scattering force, which originates from a small reflection we have, this mismatch of refractive indices between the suspending medium and the particle. It's considered here in this lower figure, because if the particles pull onto the axis and propelled, it's not being trapped. And Ashkin realized we could trap particles by not having a collimated beam, but by focusing very strongly. And show this here using these rays originating from the wings of the beam, the edge of the aperture, the lens being focusing the beam. And again, we see this deviation in the trajectory of the rays, the transfer of momentum. And we see here with these black arrows, delta P, this results in a net transfer of momentum, which acts on the particle based towards the focus, geometrical focus of the laser beam. As well as that, there's this contribution from the scattering force, which originates not in refraction, but this small reflection that we have at the surface. And while the force originating from refraction is pulling the particle towards the focus, the force originating from reflection, so the scattering force is trying to push the particle along. And so we win out with trapping if our gradient force, one that depends on the gradient of intensity of the refraction, pulls the particle towards the trap. And this can be achieved by high numerical aperture focusing. Okay, so hence we do this under a microscope, use a high NA microscope objective to focus the beam into the small diffraction limited spot. So we can use ray optics to calculate the forces acting on microscopic particles in this ray optics or geometrical optics regime, shown in this figure up on the top right here. We sum the contributions of all the rays incident on the particle, and this first shaded box it's essentially saying that we take the contribution of all rays and we sum the contributions from refraction, so the lensing effect of the rays. It crosses the interface, which gives rise to the gradient component of our force, and the contributions from the small reflections that we have. That's give rise to the scattering force, and we do that for each instance of the ray on the surface, on the interface of the particle, and sum all those up. And usually, just the first couple of refraction events are enough to get a reasonably good approximation to the force. Of course, we have a continually small reflections continue each time the ray is incident on the surface, and so this summation does go on for strictly for a very long time, but we can truncate after the first few events. That gives us a pretty good approximation in that case. Now, going back to I said I'm going to do 2 approximations, going to the very small size range. In that case, we can treat our particles as point dipolar particles, in which case we can then consider the interaction of the electric field of the laser beam with the induced dipole moment that laser beam induces in our small particle. And there we have a force of the dipole approximation, which has the dA at the bottom here. And what we find is that, yes, again, we have a force that depends on the gradient of intensity, which is this part here, but the gradient of the square electric field. Alpha here is the real part of the polarizability. And we have a scattering force, that's this second term here. S here is the pointing vector, it's the direction of energy flow down the laser beam. Okay, so that acts to push the particles along the laser. There's also a third term here, which is typically small, but does exist. It depends on the curl of the spin density. So particularly when you focus the laser beam with high numerical aperture, you have a spatial gradient of the polarization within the focus, and this gives rise to a small extra term within the optical force. Okay. Now, both of these approximations, these extremes of the size regime, explain the same sort of behavior. We trap the particle at or near the focus of the beam. When it moves away from the focus, it feels a force that pulls it back. That's proportional to its displacement, so it works very much like a mass on a spring. That's confined in all 3 dimensions. Like a mass on a spring, but particularly when it's suspended in water, very much over-damped. Okay, so it doesn't oscillate around its equilibrium position, but if it moves away, it gets pulled back by the optical forces. I said those are sort of extreme size regimes. Very often in optical tweezers, we use, or sometimes those size regimes, sometimes we use particles that are rather in the middle. In that case, to get an accurate calculation of the optical forces, we have to do a full rigorous electromagnetic scattering theory. Essentially, in just a very few words, when you solve the electromagnetic scattering problem using the T matrix method is very used. We look at the redistribution of the laser beam that occurs on scattering from the particle, and that redistribution of the field corresponds to a redistribution of momentum within the field, and hence there's equal opposite transfer momentum to the particle, which we can use to find the optical forces that are exerted on the particle. Now, I rather like the figure on the right here, because this shows calculations of the stiffness of the optical trap. I said it's behaving like a mass on a spring, so you can characterize optical trap with a parameter is essentially the stiffness. Where the dotted line is a dipole approximation, so a small particle approximation. The dashed line is a ray optics, so a large particle approximation. And the red line is a calculation using the full electromagnetic scattering theory. And this is the stiffness as a function of size of the particle, fixed wavelength. And what we see is a very nice agreement between the dipole approximation and full scattering for small particles, and nice agreement between the ray optics approximation and full scattering for large particles. So we see those 2 extreme size regimes matching up with the exact calculation. And of course, you get some deviation in around about the middle of the size range. So there's a very quick introduction to the background behind optical tweezers, and if actually I'd quite like to have an optical tweezers. They sound great. Where can I get one from? Well, you can purchase kits these days from Thor Labs, or you can build your own if you like. So I'm very grateful to Pepe Giuseppe Pesce here, who put this video together for essentially how to make an optical tweezers. As a lot of exposure, you can start on a nice vibration isolated table, and basically constructing a microscope. You can build your own commercial microscope if you wish. Or this is essentially building a homemade microscope. They've got a manual stage, important if you like have a piezo stage for sort of nanometer precision positioning of your stage, and we build up the microscope stage now to have the the condenser for illumination. There's our objective, the important part of the tweezers, high numerical aperture gives us strong focusing. Install a light source, which we need to illuminate, and prepare a sample, put it on the stage. Of course, we want to visualize this, have a condenser lens which focuses the light onto the sample, and then we need to extend that beam path through the sample around onto a camera for visualization. And here we see this yellow line here is supposed to indicate that the beam path, the illumination light through the sample, and focus onto the camera by the tube lens. This is essentially a homemade microscope, really, where you can view particles under the microscope and do the microscopy, track the motion, and so on. If you want to turn into optical tweezers, what you need to do is take a laser beam and essentially shine the laser up through the microscope, going up through the objective lens, which will focus it into that nice small spot that we need for optical trapping. So we put in a telescope which expands the beam to fill the back aperture of the objective. In it goes the microscope, up there through the objective. It's focused. This is an optical tweezers in this video here. So now that shows our particle in the center is optically trapped. It stays still in the middle of the field of view, while everything else in the background is there doing Brownian motion. Okay. And that's nice, big qualitative demonstration of trapping. We can get quantitative information out if we can track the position of the particle. So this system here is being added, essentially track the issues of the quadrant photodiode to follow the position of the particle. If you track the fluctuations of the particle in the trap that does a Brownian motion, you can calibrate it to extract that figure of merit, like that spring constant that describes the stiffness of the optical tweezers. So very quick introduction to building an optical tweezers, doing it in real life, which will take a little bit longer than the 2 minutes or so we've had there in that video, but that hopefully gives you an idea of, if you haven't used optical tweezers before, what an instrument might even look like. And what can it be applied to? It's a graphic here showing a range of objects which have been trapped with optical tweezers and reported in the literature over a size range, the logarithmic size range down the bottom, going down from atoms up to 10 micron scale of eukaryotic cells there. And so you'll see there are a number of biological objects, biological particles there, through the size regime from single biomolecule up through sperm cells, bacteria, and eukaryotic cells, sort of the large end of the size range. So we're going to concentrate on biological objects for this talk, and just a few experiments using optical tweezers for biology. And biological applications are what really go back right to the very beginning. And so Ashkin's citation that you notice in his Nobel Prize was for optical tweezers and their application to biological systems. Now we saw the first optical tweezers paper published in 1986. Just the next year, 1987, we have an application of optical tweezers to trapping biological material. Ashkin reported this work in Science, trapping both viruses and bacteria. So it's tobacco mosaic virus and E. coli bacteria. Using an argon ion laser, so it's a green laser light, it's water immersion objective, focused strongly into a suspension of the particles, that would be the virus particles or the bacteria. And the graphic on the right here shows the intensity, scattered intensity from the particle in the trap that's collected at 90 degrees. And you can see these steps in the intensity which correspond to objects entering the trap. So it's sensitive to the number of, in this case, the virus particles in the trap. Actually, it's a Science paper from 1987, so just a year after Tweezers' first paper. But in the same year, we have another publication from Ashkin in Nature. Right, if I had a science paper in Nature in the same year, I'd probably retire at that point. Okay. But it's another good application for biology. Now, the difference with this experiment is that the laser source is changed. Right? This is now using an infrared. There's an infrared laser light. This is the reason for this is that biological material does absorb light, and this can lead to damage. There is a reduction in the absorption coefficient once you get into the infrared. Okay, so switching the laser source from the green light of the argon ion laser to infrared helps reduce the chances of optical damage. Okay. And in this paper, in nature, Ashkin observed the trapping of a range of different biological materials while not damaging them. So again, trapping E. coli bacteria, but they maintained viability and still reproduced. Trapping red blood cells, manipulating organelles within cells as well. So right back at the very beginning of optical tweezers in 1987, being applied productively to the study of biological systems. Okay. So that's where we want to go with this seminar and look at applications of optical tweezers to biology. Okay. So let me tell you about some experiments that we've done at UCL. Okay. And there's a video here from one of our experiments, which is trapping and stretching, so deforming human red blood cells using optical tweezers. And before we look at the experiments, let's look at some of the theory and the modeling. Okay, so I introduced the ray optics method for calculating the forces on the spherical polystyrene microspheres at the beginning. And this work is done by Ricardo, who was a PhD student with me. He's just successfully defended his thesis and carrying on with his career. It's in Switzerland at the moment. He performed many simulations using ray optics to calculate the trapping forces exerted on red blood cells to understand the dynamics of trapping, the orientation and the equilibrium of red blood cells in the trap. So this is an animation that shows how the simulation is done. We take a converging pencil of rays, look at their interaction with a very much non-spherical object now. It's a characteristic biconcave disc for the red blood cell. And look at the refraction and reflection events that happen at the interface and evaluate the transfer momentum and use that to calculate the optical trapping force. So let's look at the force. So if we consider here the movement of a red blood cell, it's represented at the top here. This is our red blood cell in a particular orientation. The red dot there indicates the location of the focus. So what Ricardo has done here is translate the cell, in this case parallel to the x-axis, through the focus and evaluate the optical force acting on the cell. In particular, we look at the force in the x direction as a function of x. As this form here, this is the blue line on this curve here. This is the total force. The lower graph show decompose into the scattering and gradient contributions. Now what we see here for the equilibrium position, well, the equilibrium position is where the force is 0 but has a negative gradient. Okay, so we see two crossing points on the axis here and here. So there would actually be two possible stable positions in the x direction for our cell. And we think about, oh yes, this seems right because our cell is thicker near the edges, and so the beam essentially grips the cell on the thicker part, not near the middle of the disc. Okay, so translate the cell parallel to the x-axis, and evaluate the forces as a function of x. You also translate the cell up along the z-axis and find the equilibrium position there. If I play that movie as well. So here now we're particularly interested in the force in the z direction as a function of z. And it's slightly more complicated in the x direction because the crossing point of the axis is less well defined due to the way the scattering force and the gradient force behave, which is really a consequence of the shape of the object. We're no longer a spherical object. It's a characteristic biconcave disc of the red blood cell. The gradient is quite shallow around about the crossing point. And in fact, it looks as though the cell could indeed fluctuate up and down the axis with little change in the optical force that acts. So we should ask then, is it possible to trap our blood cells along the z-axis with the shape? Well, what we need to do also is factor in, actually the cells have a finite weight. Okay, so this is only the optical force contribution. Okay, when we introduce the weight as well, it'll tend to make the cells sag slightly in the trap. And that means essentially we need to shift this whole force displacement curve down a little. The weight is approximately a piconewton for a single red blood cell. And that leaves us with a more well-defined zero crossing point of the force displacement curve. And allows us to understand that, yes, we do indeed trap the cell in the vertical direction but only if we take into account the fact that our cells do have a finite weight, and they do sag down slightly in the trap. And it's important that we include that in order to understand how and where the cells are trapped. Because the cells are non-spherical, then in addition to a force, there's also a torque which tends to align and orient the cells in a particular direction. So we see, look here at the torque around the x-axis. So again, here the red dot indicates the location of our focus. As we rotate the cell, again we see that the torque is a negative gradient with a zero crossing at some particular orientation of the cell. And that corresponds to the cell in the orientation that I showed in the previous videos. That's why that was chosen. Right. And then we look at rotations around the z-axis. Now, if we have just a single beam, you can imagine it gripping the cell on one side of the thick part, then the cell's sort of free to flap around that axis. And so what we actually need are two beams. We've got two beams as shown by the locations of these red dots here, and this then provides that confinement around the z-axis. And so we evaluate the torque as a function of that angular rotation. And I say, yes, these two beams hold the cell in that orientation with the plane of the cell that's lying in the XZ plane, I show. And that is indeed what we see in experiments. Now, Ricardo did all these experiments with ray tracing, and partway through his PhD, he attended a conference, and there he met another PhD student, David Bronte from the CNR in Messina. And David's been working on machine learning methods for optical tweezers calibration as part of his PhD. And yeah, Ricardo got together and they thought, well, perhaps we can apply this to Ricardo's problem of calibrating the optical tweezers for the red blood cells as well. So together they trained a neural network. So the parameters, there were 6 input nodes which correspond to the position and orientation of the cells, 6 output nodes, which are the forces and torques, 7 hidden layers of 256 nodes each in between. And they trained this neural network on the ray optics calculation data that Ricardo provided. And there you see the agreement here between the forces and the torques calculated by the neural network and the geometrical optics methods here. Characterize that with the normalized Riemann square error there, which you can see is fairly small and indeed improves with the number of rays that we consider. Now, increasing the number of rays generally increases the computation time, and the great advantage of this using the neural network here is that it vastly reduces overall the computation time, in fact, by a factor of about 100. So when we perform a simulation of a red blood cell within the optical tweezers, about 5,000 time steps to look at the dynamics of the cell and how its position and orientation fluctuate within the trap, and a vast improvement of speed by about a factor of 100 by using the neural network method. Okay. So that was done, as I said, by 2 PhD students, David and Ricardo, together, who met at a conference. So we want to implement trapping experimentally. So here's a little cartoon that shows what happens, what we see in experiments, and now we can relate that to the forces and torques that are experienced by the cell, as we now understand geometrical optics. This is supposed to indicate the cell, and these blue light cones supposed to show the focused laser beam. The cells are initially lying flat on the surface. When we position the 2 laser traps on top of the thick stuff, and they flip into that orientation because of the optical torque that we just see evaluated there. And those 2 optical tweezers that pinch the cell on the thickest part around the edge and hold it in that orientation. Now, the question is, why are we interested in trapping these cells? So these experiments arose when a colleague approached me and asked, is it possible to trap and indeed stretch red blood cells? And he was interested in a condition called diabetic retinopathy. And this is a condition that affects patients who have diabetes, type 2 diabetes. And there are a lot of people who have diabetes. So projections, well, there were 350 million worldwide patients with type 2 diabetes. Back in 2015, projected to be something like 550 million in 2030. So hundreds of millions of people with type 2 diabetes. And patients who live with diabetes for 10 years or more are often affected for 80% of them affected by this condition, diabetic retinopathy. And this affects eyesight. And in the early stages, patients experience blockage of the small arteries in the retina. And in the later stages, and these blockages called retinal ischemia, so this is basically death of the cells in the retina. The body tries to grow new blood vessels, they're abnormal, they grow out of the retina, they burst, they leak into the eye. This obscures the vision. And in fact, diabetic retinopathy is the leading cause of new cases of blindness in the USA. And so Rupesh Agrawal, my colleague, said, well, a theory that this is a result of a change in the mechanical properties of the red blood cell. Since your red blood cells are around about 8 microns diameter, the smallest blood vessels in the eye are about 5 microns. The suggestion is that if the cell is less deformable, it can no longer squeeze through those small blood vessels. And if we look at the numbers here, an adult human has tens of trillions of red blood cells. They go around the body in about a minute, and each blood cell has a life of 120 days. So any red blood cell, I think, has a pretty good opportunity of trying to pass through those small blood vessels many, many times. And if they're not able to deform and fold and squeeze through those very small blood vessels, yeah, surely it's very likely that they will lead to blockage. So this seems like a viable hypothesis, we thought. So we should test this. And I like these experiments because we were able to do this with actual samples from patients who presented at the Moorfields Eye Hospital in London. And as part of their routine checks, we asked to donate blood for this study. We took them from blood from patients who have diabetes but have not yet developed retinopathy, patients with diabetes who have developed retinopathy, and we need a healthy patient control group as well. These are all subject to their regular blood tests, the biochemical and hematological blood tests. If you're interested, all these tests are here. Essentially, there's no difference between the healthy and control groups. These bloods are then sort of hopped on the tube in London, 2 stops down the Northern Line in London, and appeared in our lab in the physics department with some patient samples. So we put them in the optical tweezers. In our optical tweezers for these experiments, we want to create 2 beams, because as we saw, this gives us control over the position and orientation of the red blood cell. So our setup is that we have a laser. The beam is split into 2 and recombined using polarization optics. And in one branch of that, we've got these galvanometer steering mirrors. So these are rotatable mirrors under computer control. And the rotation of the mirror corresponds to a translation of the beam under the microscope. Yes, this means we can move the location of one beam with respect to the other. So we trap the red blood cells, and as we now understand, they flip in the 2 beams, and we view them sort of edge on each other. And then, because one beam can be moved, what we do is the right hand beam in the right hand trap here, we increase the separation between the traps. So we move that beam out to the right there. It's gripping the red blood cell, that stretches it. And that's what we see here. We see the cell being trapped, stretched, and then we release it, it relaxes back to its equilibrium length before we catch it and stretch it again and repeat. So we get quantitative data from this by from the video, where we're able to detect the cell boundary that's shown in this picture here. And here you can see superimposed the initial cell boundary and in its fully stretched state. So you can see that we really are stretching the cell. As a shift in the center of the mass of the cell as well. And in this case, we're then able to track the length of the cell, obviously the change in the length of the cell is shown here. So the red line shows how the traps are moving apart. The blue line here shows the extent of the cell. So you can see it really is stretched as the traps move apart. Then what we do is we jump the trap A to a large distance, and that allows the cell to relax back to its equilibrium length. And we do that many times, typically a cycle of 10 stretches the cell, and go away and find another cell with a cycle of 10 stretches there. And look at that distribution of initial cell lengths and sorry, actually, this is the central mass. So it's showing the displacement of the cell within the 2 traps as we do the experiment. So here we have our distribution of the stretch lengths against the initial lengths. On the left, we have our healthy control. On the right, we have our patients with diabetic retinopathy. We can see that their data appears to be clustered around a straight line in both cases. It's a little difficult to understand from just that sort of plot there. So what we do is to define some sort of deformability, which is essentially the fractional change in cell length in each cycle. So it's fully stretched length, subtract its initial length and normalize that by initial length. Now we have here a kernel density estimation of all the measured deformabilities of all the cells that are all subjected to the same stretching protocol. Okay. And we have the black line here represents our healthy control patients, and the red line here represents our diabetes patients. And what we find is that there's a shift to lower deformability, and that shift, because of the number of cells we have, the number of stretching events that we're able to measure, that shift, if it's small, is statistically significant. So our diabetes patients do have cells that are less deformable. Now all these experiments were done by Tom Swart and Chris Richards, two PhD students in the lab. Tom graduated his PhD, went on to do a postdoc actually at the Institute of Ophthalmology. Chris did his PhD and now works making banking software. Actually, he's not in science anymore. But two very good PhD students. The experiments are just one contribution to their overall theses that they wrote. Okay. So for our diabetes patients, we're able to measure this statistically significant claim decrease in deformability. So this perhaps lends support to this idea that diabetic retinopathy is perhaps linked to the change in mechanical properties of the cell. Maybe they can't squeeze through the small blood vessels. But as well as diabetes patients, we also investigated this condition, Birdshot chorioretinopathy, BCR. Description there, perhaps the important phrase to note here, it's an uncommon bilateral inflammatory disease. The number of patients presenting even at the Moorfields Eye Hospital, the UK Centre for eye disease, right? The number of patients is relatively small, so difficult to be quite so sure about the statistics that we have here of the patients. But the importance of these patients to the study is that although there are many manifestations of birdshot, as we call it, unlike diabetic retinopathy, it is not very rarely reported to be associated with the sort of thrombosis and vascular occlusion, so blockage of the blood vessels in the eye that you get with diabetic retinopathy. Okay, so it affects the eyesight in many different ways. But we don't see a similar blockage of the small blood vessels. So very briefly, here we were able to obtain cells from a few patients who presented in the eye hospital with BCR. But doing all the biochemical and hematological tests, there were differences here in the neutrophil count and chloride level. But we tested all the cells with the same stretching protocol. And in this case, we found that there was no statistically significant difference in the deformability. Okay, so we will suggest here that this perhaps may account for the fact that Birdshot patients have a very low risk of thrombosis, of blood cells blocking the small arteries in the eye. And perhaps that supports our hypothesis that our diabetes patients do have an elevated risk, which is due to a change in the mechanical properties. I mentioned briefly something else that we were interested in. We talk about red blood cells and the mechanical properties, and one condition that is then very often mentioned is that sickle cell disease. Okay. Now, sickle cell disease is a genetic disease, in fact, the most common monogenetic disorder. Around 300,000 children are born every year with sickle cell disease, named for the very characteristic sort of curved crescent or sickle shape of the cells. They are less flexible, less elastic. The genetic defect affects the ability of hemoglobin to transport oxygen, and it's believed that these factors together lead to the the sort of pain crises that sickle cell patients experience. So we think that this will be an interesting system to study. Okay? We haven't done experiments. What we have started to do is look at the optical trapping by means of simulations, ray optic simulations that again Ricardo has performed. Now here, change in shape of the cell makes this extremely challenging. Okay? So we first of all orient the cell in this sort of flat configuration, okay? And allow essentially a simulation of the dynamics of the cell in this trap. So we, at each time step, we evaluate the optical forces acting on the cell. We give a Brownian kit, change position and orientation, and use that to evaluate the resultant position of one of these sickled cells in the same trapping configuration. It's got these two links. Okay? And it seems to show an equilibrium position. In this case, it's pushed slightly up the axis by the radiation pressure on the beam, but maintaining this orientation. However, the situation is not quite so straightforward because the shape of the cell, the graphic on the left there shows the correlation of fluctuations between the 3 position coordinates and the 3 angular coordinates. And perhaps I could draw your attention to place like here. For example, we see this correlation between translation in the x direction, and this is the angular rotation beta. That's a rotation around the y direction. So as the cell fluctuates in the x direction, that also changes its orientation as well. Okay, so position and orientation are correlated there. And this gives rise to some more complex dynamics in the trap and leads ultimately to the fact that there are multiple stable trapping and orientation positions for a sickled cell. So this is unfortunately isn't an animation, but as you see, there's actually a stable orientation where the cell is sort of flipped, so we're looking at it sideways along the crescent here. Okay. So the sickle cell is a more challenging system to study experimentally. It was very challenging to model because of the irregular shape, and Ricardo did a fantastic job on this. But also more challenging to study experimentally because of the consequence of the shape. It has these multiple stable trapping positions and orientations in the trap. I'll move quickly on to some other experiments. So we worked with Eva Palach, who at the time was at UCL, is now at Cambridge University, to use optical tweezers to make some measurements which are now not whole cell measurements. Okay, so when we did those experiments on the red blood cells, we were sort of treating the whole thing like an elastic object that we could stretch. But now using optical tweezers just to measure properties of the membrane itself. And the target system are pluripotent stem cells here, derived from mice. Now, my limited knowledge of stem cells, when we started this, was that stem cells is a precursor and they undergo this transition towards their state, just their final function. And this change includes a change in shape. So they go from this sort of spherical shape to this extended shape here. And that requires a change in mechanical properties. And so as the cells leave their initial pluripotent state, this is driven by something called ERK, extracellular signal regulated kinase. It's taken up by the cell, as well as a decrease in the membrane tension. So the membrane tension, the stiffness of the membrane changes, promotes an uptake of ERK, and that allows the cell to make this transition to its final state, accompanied by this shape change. So how can we measure the properties of the membrane? We do that using optical tweezers. Okay? So Eva approached us and asked if we could assist in building optical tweezers that was capable of doing this sort of measurements. The measurements themselves were done by Henry Diabetic, who's a PhD student with Eva. He's now in San Francisco and is continuing, I believe, to do some work with optical tweezers. So these experiments progress that we have a bead, a coated bead, that adhered to we have the embryonic stem cell, and as we retract the cell away from the bead, what we do is we pull out a long, thin tether of membrane. And that membrane stretches and stretches until eventually it pulls the bead out of the trap. And from the extent of the tether, and its maximum limit, and from what we know is the optical force pulling on the bead, because we can measure the displacement of the bead in the trap. From those parameters, we can calculate the membrane tension. And what we find is that the change in shape at some time, it's the time here T8, 1624, is this number of hours after it's put into the culture medium. What we see is a decrease in the trap force. Okay, required to pull the tether from the membrane, so a decrease in the membrane tension. That's regulated by a beta-catenin, and that decrease in the membrane tension then leads to an increased activity, the extracellular signal regulating kinase. Okay, so there's a lot of biology and biochemistry behind that. I'm going to limit myself to discussing the optical tweezers measurements here. Okay, so we are able to use optical tweezers to exert a force and pull a tether to investigate just the properties of the membrane. So no longer the whole cell as we did for red blood cells, and we can quantify the membrane tension and the parameters that affect the membrane tension. We found that indeed this is triggered by the reduction in beta-catenin, and that then allows this increased activity of the ERK, and then shape change of the cell as it goes from its naive pluripotent state towards its final form. Next slide. What I would like to now talk about are some future work, some work that's going in other groups that I think is particularly exciting. Okay? And I'm going to highlight a couple here that I really like very much. The first one is, this comes from Lynn Patterson, so I mentioned Lynn earlier. I said we worked on this article for the roadmap optical tweezers, and Lynn's very kindly allowed me to put some videos and images in this presentation from some of the latest work, which has just gone onto bioRxiv just in the last couple of days, I believe. And these experiments, they integrate multiplane imaging, which is what's being shown here. So imaging of a trapped particle in 9 different planes, this scanned through the focus, combining it with light sheet microscopy. And this multiplane imaging permits Lynn and her colleagues, particularly Amanda Wright in Nottingham, to track the particle in 3 dimensions and use that for microrheological measurements of the environment in the immediate neighborhood of clusters of cancer cells. So I think this is particularly exciting because what we have is a technological development here, particularly in terms of tracking the particles in 3 dimensions and then measuring the rheological properties, particularly in the region surrounding a cell, and looking how that evolves over time in order to address a biological problem. So when I talked about the stem cells, we saw how the cell interacts with its environment in terms of an increased uptake of ERK and indeed FGF, growth factor. But these experiments can also reveal how the cell impacts on the environment as well. It's very significant here in the case of cancer cells. So I think this is extremely exciting work. I say that the Lynn has just put out on the bioRxiv, combining light sheet microscopy for deep imaging with these measurements that can be performed over a very long term to look at these changes in the local rheology in the region of these clusters of cells. Okay. So I think this is I think a very exciting development, and I think a great example of how advances in technology can overcome particular experimental problems and then open up new questions in biology as well, to look at how the cell affects its environment as it grows. Okay. So I'm very excited about this work. I'm very pleased and grateful to Lynn for allowing me to include these pictures, and particularly the postdoc, Tanya Mendonca, who's done much of the work on the instrument before it's moved to Nottingham. And then another example, I appreciate I'm coming towards the end of my hour, is not natural biology, but synthetic biology. So it's something I think is a fascinating area. And these videos here have come courtesy of Yuval Alani in chemical engineering at Imperial College. Whereas Yuval synthesizes giant vesicles to behave as if you like, almost like synthetic cells. So they are relatively large objects, 10 microns so in size, or larger, giant unilamellar vesicles made by these sort of microfluidic methods that we're seeing here. And then we have the potential for using optical tweezers to manipulate and probe the properties of these vesicles here. So you can use optical tweezers to, for example, trap vesicles and bring them together and look at adhesion. You can use optical tweezers to create networks of these vesicles. So you see here, this video being steered into a network in a straight line, but the advantage of optical tweezers, we can move the beams around, we can move objects around, we can reconfigure the way in which these vesicles join up. Now, particularly exciting then is that once the vesicles have been joined, they can be stimulated to fuse. This is done with the presence of golden nanoparticles on the surface, which are heated up by another laser beam. And this is already playing top right. They fuse and the contents mix. Okay. And I haven't shown it here, but in some other experiments from Yuval's group, they're showing a fusion of 3 vesicles, which contain the transcription elements and all the sort of ingredients, if you like, that are required to synthesize GFP, green phosphorescent protein. And at the end of the experiment, yes, they see that the protein has indeed been synthesized within the resulting large reaction vesicle. So almost like cells being induced and coming together, so but synthetically. You can also pull out membrane tethers, just as we saw in the stem cells in the previous experiments. Here we've got one of the vesicles attached to a trapped bead being pulled along. You might just be able to make out that bright line in the fluorescence microscopy. It shows the membrane tether being pulled out. And just as for the case of the stem cells that we saw previously, we can use the parameters of the tether, the extent of the tether, and the force that's being applied by the trapped bead to understand the mechanical properties of the membrane. Other exciting work I know Yuval is working on, looking at phase separated systems in membranes. So you have so-called liquid ordered and liquid disordered phase within the bilayer, and that can indeed be trapped and manipulated and moved around in the bilayer. You might be able to just see it being trapped in that top video, and then moved around. It's moving the liquid ordered domain around within the liquid disordered domain, and indeed it can be stimulated to mix those domains and then demix again. It's sort of an analogous to the presence of lipid rafts in the membranes of real cells. So again, this is an area I think is particularly exciting, moving into the regime of synthetic biology, creating objects that can potentially mimic real cells, or at least some of the functions of real cells. And obviously optical tweezers have a role in these experiments as well. So I am coming to the end of my hour, which has gone all too quickly. There seems to be almost too much to fit in that. I'd say just a few examples. If I can just say about a couple of things that we're also doing in the lab at UCL, as well as optical manipulation, we're looking at acoustic manipulation in a microfluidic channel. These are 2 micron particles flowing down a channel, and then we use an acoustic standing wave to essentially focus that stream of particles. It's something we'd like to eventually use at much lower density for to isolated bacteria interested in antimicrobial resistance. Do things like deforming and stretching microemulsions, and optical binding, which is this sort of formation of multiple particle structures that we see here, but that's a whole another hour of seminar, which I can't remember. I should mention that the videos of acoustic manipulation were created by Anna Jorgensen, who is a student on the Transformative Pharmaceutical Technologies PhD training program, doing all kinds of rotation projects in the lab. Great work in a very short length of time. So I will finish because it's now 1 o'clock. So there's many people I have to thank, and I say in particular that the people who really spend the time in the lab and doing the simulations, the students, PhD students and the postdocs, so Chris, Tom, Nick, Ricardo, Sandrine, Anna, they do the work that I sit in front of the screen and tell you about now. And so I also want to thank all the collaborators, Rupesh and Carlos for the red blood cell stretching work, even for the stem cells, Lynn for allowing me to talk about how multiplane imaging work, and Yuval for allowing me to talk about his synthetic biology work. Onofre and David, Onofre I've known for many, many years, so we've worked together on many projects over that time, and his PhD student David, who worked on the neural network training for this calibration. And we saw earlier. And if I just finish, as I usually do, with a mention of the book, but mainly for a mention of the website, because many of the figures that I've used, and indeed the code for doing the simulations of optical trapping, and indeed that video for the construction of the optical tweezers can be found at this website, and it's all there. And you can download particularly the MATLAB software for optical tweezers, calibration, interface and video tracking, and so on. That's all on our website, and it's there to download.